We have all seen the cinematic trope. A skyscraper window shatters and a violent suction effect instantly yanks papers, furniture, and people into the open sky. This visual works because it exploits a common misconception about high altitudes. At ground level, gravity pulls things down. We often assume those rules must change as we move further into the sky. To test the idea that gravity weakens with height, we can look at the top of the world's tallest building. At the apex of the Burj Khalifa, you are over 2,700 feet further from the center of the Earth than someone on the sidewalk. The actual quantitative difference in gravitational pull at this height is roughly 0.03%. That change is completely imperceptible to humans and has no effect on the weight of office furniture. Gravity's downward pull remains absolute regardless of the height of the building. The force pulling objects horizontally out of a window is an entirely different, unseen physical mechanism. Some theories reach for more exotic explanations, like Albert Einstein's concept of gravitational time dilation. While time does pass faster at high altitudes, the difference between the ground and the roof is measured in microseconds per year. This effect is too small to have any impact on the physical world of a skyscraper. Standard gravity and time dilation cannot explain the phenomenon. We are left with a mystery, a massive, invisible force physically shoving objects out of buildings and into the sky. At these heights, air behaves like a fast-flowing river. Rising above the friction of trees and hills on the ground, it accelerates, often moving 40% faster near the upper floors. The Bernoulli principle states fluid speed and pressure are inversely related. When wind hits a skyscraper's face, it slows and piles up, creating a high-pressure pushing zone. But as air whips around the sides, it accelerates, creating active low pressure, or suction, along exterior walls. Air trapped inside a climate-controlled oven is at standard atmospheric pressure, but next to the fierce, low-pressure vortex whipping past the exterior glass, that perfectly normal interior air suddenly becomes a massive high-pressure zone. Internal air pressure seeking equilibrium violently pushes objects through the opening. The building's own internal atmosphere provides the force that drives equipment out through a broken window. The 1970s John Hancock Tower disaster in Boston provides a historical record of these fluid forces in action. During its construction, the tower began losing its heavy glass windows, which cracked and fell hundreds of feet to the street. Patches of plywood soon covered the facade, earning the building an embarrassing nickname. Investigation revealed a material science flaw. The windows were built too rigidly to accommodate thermal expansion or vibrations caused by wind. This extreme rigidity caused microscopic cracks to slowly form and propagate at the very edges of the glass. Once compromised, the pressure differential between the interior and the low-pressure suction outside blew panels out of their frames. The Hancock disaster demonstrated that skyscraper facades must be engineered as dynamic components, capable of moving in response to invisible fluid forces. To prevent similar failures today, engineers utilize physical scale models of skyscrapers and their surrounding cityscapes in massive wind tunnels. Engineers also use computational fluid dynamics, or CFD. These supercomputer simulations map complex pressure vortices across the entire digital surface of a building before a single physical model is built. Architects use this data to alter the physical shape of the building. Tapering the profile or adding strategic openings breaks up vortices and reduces the wind load on the structure. Structural design now utilizes building geometry to steer air currents around structural weak points. Modern window systems use flexible laminates and gaskets. These components allow the glass to shift within its frame, absorbing wind energy rather than rigidly resisting it. Stabilizing slender skyscrapers requires an internal countermeasure known as a tuned mass damper. This diagram shows how the damper acts as a pendulum. A weight of several hundred tons sways in the opposite direction of the wind's force, acting as a shock absorber to cancel out structural motion. Unexpected wind events, such as the 2024 Houston derecho, prove that managing fluid dynamics remains a continuous engineering challenge. A skyscraper is a mechanical assembly of dampers, gaskets, and aerodynamic shapes designed to react to its environment in real time. We are seeing a building maintain stability through engineering that works in concert with the wind.